Hi everyone. Welcome to another video by Cheenta. I am Rajdeep. Today we'll continue the ongoing number theory series in the Diophantine direction. In that, I will talk about solving equations over the integers with integer solutions. This is a very broad part of number theory, and so obviously I cannot cover everything. And in fact, I'll go as far as sacrificing many other techniques such as Fermat's descent, parity checking, and many other small things that you can pick up. What I will focus on for the next few videos is solving equations modulo p. This is a topic I've already broached upon, is that uh, many times when you have an equation you want to solve, you want to look at some, you want to go modulo some reasonable modulus and see what data you can derive from it. So that's the line I'll take. My goal here at the end of this endeavor, maybe 3-4 videos, is to introduce you to the legendary symbol and perhaps even touch upon quadratic reciprocity. But before we get there, we have to build up to it. And so today's lecture will be on orders modulo of prime. And I hope you enjoy it. And let's get into it. Right. So as you can see, the topic is sort of the larger theme is solving equations modulo b. I don't have to justify why we care about this. I've done that many times before. In particular, we'll look at this problem from the MOP 2011. For those of you who don't know, the MOP is essentially the American equivalent of the Indian IMOTC. It's the thing, it's this camp that American students can attend after they've done, a good performance on the USAMO, the US National Math Competition. Right. So it's a tough problem, as tough as they get. And the question says, let p be a prime and n a positive integer. Suppose that p to the 1 fully divides 2 to the n minus 1. And they justify that what fully divides means is that it's divisible by p, but not p squared. The exponent of p that shows up in 2 to the n minus 1 is p, not a higher power. If this is the case, prove that p to the 1 also fully divides 2 to the p minus 1 minus 1. The highest power of p that shows up inside this guy is 1. Uh, Obviously, as usual, pause the video and try it on your own. I will not, as usual, get into it directly. Rather, I will sort of take a more leisurely path to it, um, starting with the idea that of solving equations modulo p. Sort of a quick sort of journey, if you will, of why is this a thing that we care about. If you remember, this is something I've done in one of my previous videos, is that we develop newer and newer number systems. We broaden our horizons by asking sort of polynomial questions. So you start with the natural numbers, or even the whole numbers, if you will, which are just 0, 1, 2, and so on. You get the integers by asking the question, can I solve x plus 1 is equal to 0? Inherently, you can't. Inside the naturals, there is no number which you can add to 1 to get 0. So that's why you invent a new thing and you call it minus 1. And then you extend it. And so that's how you get minus 1, minus 2, so on. That's how you get the integers. Then you ask the question of, can I solve 2x plus 1 is equal to 0? There's no integer that solves this. So I have to make up something new that works. And that's how you get the rationals. I've said this before, the jump from rationals to reals is not a polynomial jump. It's a different kind of a jump. It's an analytic jump, but less on that. Once you have R, somehow, say magically we have got the real numbers, the jump from real numbers to complex numbers is again a polynomial one. It occurs when you ask the question, can I solve x squared plus 1 is equal to 0? There's no real number that solves this, so I'll make up a new thing that does, and that's how you get the complex numbers. And turns out that all your polynomial questions are answered inside complex numbers. That's the fundamental theorem of algebra. No matter what polynomial equation you cook up, it will always have a solution in C. So this polynomial process kind of ends at C. That's why C is also called algebraically closed. This is sort of a quick bit of trivia. The thing is, you can ask the similar kinds of questions over, numbers modulo p. So inherently, you have only p residues modulo p, right? 0, 1. These are the numbers modulo p. 0, 1, 2, p minus 1. You can ask the question, can I solve x plus 1 congruent to 0 mod p? Which is essentially our version of the modulo p version of x plus 1 is equal to 0, right? That's what it means here. X plus 1 congruent to 0 mod p. The thing is, you don't need to invent anything new when you're working modulo p. You already have a number that does this job. That's, can I solve this? Yes. X is equal to p minus 1, right? Generally, we have negative numbers. So you don't need to invent new things to answer these polynomial questions. You don't, and sort of if you make the next jump, which is, can I solve 2x plus 1 congruent to 0 mod p, say. Sometimes you can and sometimes you can't. This sort of a question gives rise to inverses modulo p. You can make up new symbols, but we choose not to do that since, for the most part, if you're working modulo prime, everything has an inverse. So you can almost always solve this. As long as p is greater than 2, it's an odd prime, this at least you'll always be able to solve. So that's how we got inverses modulo p. Generally, if you asked me to solve a system that looked like this, ax plus by congruent to c mod p. Find x in terms of y in terms of x, right? That's a thing you can do. I can solve this as follows. I'll put, say I want to find y in terms of x. So then by is congruent to c minus ax mod p. And then I just multiply on both sides by the inverse of p. Right? We've covered inverses in a previous video. And that's it. So, and this is what we call a linear system, a linear equation modulo p. So linear questions, are easy to answer. 1-degree questions are easy to answer modulo p almost always. This step you won't be able to do if b was 0. But if b was 0 mod p, this is a silly question. You can just it doesn't mean anything. Like it's an you can't find the answer in that case because this term alone vanishes then. So yeah. So obviously the next jump is quadratics. And even higher powers for that matter. Quadratics and above. You can ask the question, can I, solve x square is equal to 2 mod p? Turns out, sometimes you can and sometimes you can't. When you can, you say that, so if there is actually some number modulo p, such that some number say a modulo p such that a square is congruent to 2 mod p, and that can happen. We have seen it, right? For example, if you went mod 7, this is an example I took up in a previous video. When you go mod 7, 3 square, which is 9, is congruent to 2 mod p. So 2 has a square root mod p. I don't have to invent something new. It's already in the system. So sometimes you can and sometimes you can't. A square is equal to 2 mod p. If there is such a number, we say that 2 is a quadratic residue. Mod p. And the general thing is like a is a quadratic residue mod p if there's some b such that b square is equal to a mod p. That's the idea. I'm not going to go into this too much. The question that I want to address today is, can I solve this? But you will come to see that this question of when can I solve this is kind of at the heart of the legendary symbol. It is the legendary symbol in some way. The answer to that question, whether or not a given residue mod p is a quadratic residue or not. But that's for later. Today I want to focus on this question. Can I solve this? X square is equal to -1 mod p. As you recall, if we ask this question over the real numbers instead of the numbers modulo p, there are no such numbers, and so we have to invent something. You might have noticed that we are not inventing new things while working modulo p. There's no restriction. The whole thing is really it's a ball game that we invent. So nothing is stopping you from inventing these new numbers. You can, and it is a thing that people do, and it's it's in the realm of algebraic number theory. I'm not going to go there. As long as you're working over numbers mod p, I'm going to stick to what I have, which is the numbers mod p. Whenever I don't have an answer, I don't venture out looking for a made up solution, if you will. All numbers are made up in some sense. I'm going to stick to what I have. But I just want to make sure that you know that there's no harm in inventing new numbers to answer your polynomial questions. Regardless, x square is congruent to -1 mod p. When can I solve this? Instead of asking a question of given a, is a square congruent to -1 mod p? This is a silly question because I can just check this, right? Fixing a and fixing p and asking the question for a is a silly question because I can just check. What is more interesting uh, is given p, is there a number? So the point is, the silly question is, if you fix both a and p, is 2 square congruent to -1 mod p? If you fix p, is there a given p, is there, say, an x rather, an x such that x square is congruent to -1 mod? That is a cool question. In the language that we just saw, this is the equivalent to asking, when is -1 a quadratic residue mod p? And I'm not gonna do this exercise now because it's quite time taking. At this point, I do want you to try something. Pause the video, take a sheet of paper, and say try the first, let's say, 7, 8 primes. Maybe more if you have the patience for it. So start with odd, obviously. So 3, 5, 7, 11, so on. Try the first 7 primes and look for the answer to this question. Is 3 gonna have, modulo p, does -1 have a square root? Modulo 5, does -1 have a square? Answer this question, like look for an answer. It's not hard because you just have to check finitely many numbers. Just go through all possibilities, go through 1 square, 2 square, 3 square, all the way up to p minus 1 square, and just see if -1, p minus 1 shows up here, modulo p, of course, all of this modulo p. So it's a finite check. There's nothing crazy here. Make this check for, say, the first 7, 8 primes and see if you can find the pattern. I think it's a good exercise at this point, so I would urge you to pause the video and try it on your own. If you did this exercise, you would find that, surprisingly enough, there's a very neat answer. The answer to this question is yes, if p is congruent to 1 mod 4, at least that's what you would conjecture. One would notice, if you will. Yes, if p is congruent to 1 mod 4, and no, if p is congruent to 3 mod 4. And these are the only choices modulo 4 for a prime number. It's a simple check, right? It can't be 2 or 0 because in that case, any number congruent to 2 or 0 mod 4 is even, and so it can't be a prime more than 2. And so this is what you would notice as a pattern. And turns out it's a real result. Depending on who you ask, it's either called the n square plus 1 lemma or Fermat's Christmas trick or something like that. Fermat's Christmas lemma or trick. Again, it really just depends on who you're asking. And what does it say? It says that given an odd prime p, the question for the even prime 2 is obviously no, because there's only 2 numbers modulo 2. If you square them, you'll just get 0 and 1. So there's really nothing crazy there. So given an odd prime p, there exists an n such that p divides n squared plus 1 if and only if p is congruent to 1 mod 4. So that is a result. And you see why this is equivalent to what we saw. P divides n squared plus 1 is the same thing as saying n squared is congruent to minus 1 mod p. This is just a rearrangement. One direction of this, the harder direction, requires primitive roots, which we'll not see today. It's for a later video. But the easier direction requires orders. So we'll see why. The easier direction, as you would imagine, is so the easier direction is usually the direction where you'd have more information, which you somehow make it imply less information. So more information is this. This is a denser piece of information. There is some n such that this fancy thing happens, whereas this is a simpler piece of information. So usually the case would be that this is the easier way. So if you just, looked at this, n squared is congruent to minus 1 mod p. Can I deduce something about p given this data? If n squared is congruent to minus 1 mod p, then I can square both sides to get n to the 4 is congruent to 1 mod p. At this point, something should go off in your head. In particular, what should go off in your head is Fermat's little theorem, which says that n to the p minus 1 is congruent to 1 mod 4 as well. Already you start seeing something. P congruent to 1 mod 4 is the same thing as saying that 4 divides p minus 1. So there's something interesting going on. N to the higher power is congruent to 1 mod 4. N to a lower power is congruent to 1 mod p. Can I say something about those two powers? Answer is yes. And so this sort of a discussion very naturally leads into the notion of orders. Yeah. So what is the order? Given A, so given a prime P, say, we can obviously generalize this discussion to composite number, but to keep it simple, I'll stick to primes for now. Given a prime P and P not dividing A, and some A such that P doesn't divide A, we say that we define the order of A modulo P to be the smallest k, the smallest positive number k, such that A to the k is congruent to 1 mod p. You would have guessed this by now. The order is the smallest thing that I have to raise A to get 1 mod p. And if you relax this condition of p not dividing it, you run into the issue of no matter what power you take of 0, you're going to state 0. So you'd have to define the order to be infinity, which is a thing that is like legitimate. You could do that. It just unnecessarily complicates the discussion. Why does the order always exist is a very easy first question you can ask. We've already been over this in my discussion of the Fermat's little theorem earlier in this series. You just really look at powers of A, mod p, A squared, blah, blah, blah. By the fact that there's not that many choices for these powers to have, you would get A to the I is congruent to A to the j mod p, by infinite PHP, if you will. There's infinitely many elements in this sequence and only finitely many choices for what they can be mod p. So 2 must be congruent to each other mod p, which implies that A to the I minus j is congruent to 1 mod p by the cancellation rule. So there's at least, there's at least one number that works. In particular, there will be infinitely many. I didn't even need to do this. I could just say by FLT, p minus 1 always works. So you just look at all the numbers k such that A to the k is congruent to 1 mod p, and you just ask for the smallest one. In another way of thinking, the order is also the cycle length of the powers of A. If I looked at A square, A cube, blah, 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 at some point you'd hit 1, at which point the powers would restart. Right? After 1, whatever the next power is, so say this was A to the k, then A to the k plus 1 is just A to the k times A. But A to the k is 1, so A to the k plus 1 is going to be A. And so in some ways, it would restart. and then you'd hit on a to the 2k, you'd hit 1 again, and so on. So if all of these are not 1, in some way this represents all the possible powers of a. So yeah, that also kind of justifies the usage of the word order. And so one easy result that I will not prove, but it's actually pretty easy to see why this should be true, especially if you think of the order as this sort of the minimal cycle length, is the following. The order, if a to the m is congruent to 1 mod p, where, it's kind of implied that a is not congruent to 0 mod p, for some positive integer m, then the order divides m. The order of, I'm not writing it, the order of a mod p divides m. In some ways, wherever 1 shows up, it will only show up in like jumps of the order in this sort of infinite sequence. Hopefully you get my point here. 1 only shows up in jumps of the order. This is actually a pretty easy result, but it's also a very important one. In particular, it immediately solves one direction of n square plus 1 lemma. N to the 4 is congruent to 1 mod p. Also in particular, this implies this has the following corollary, is that the order always divides p minus 1. The order of any element divides p minus 1 because FLT. A to the p minus 1 is congruent to 1 mod p no matter what a is. So the order of every element divides p minus 1, which is, what we see here. So what are, if n to the 4 is congruent to 1 mod p, what are the possible choices for the order? The order must divide 4, right? Which implies that since n to the 4 is congruent to 1 mod p, so the order is either 1, 2, or 4. If n was 1, 2, or 4, it would if n was 1 or 2, it would violate this. If n was congruent to 1 mod p, then n square couldn't be minus 1 mod p. If n square was congruent to 1 mod p, then n square couldn't be minus 1 mod p. The only choice for the order is actually 4. So n to the 4 congruent to 1 mod p, given that n square is congruent to minus 1 mod p, implies that the order, which is 4, divides p minus 1. So that solves one direction of this. I understand this is a lot to take in at this point, but I haven't made any big jumps anywhere. So if you're stuck, just go back and watch the thing. It's a very natural progression. As far as this problem is concerned, the initial one, slightly tricky, but not too bad. Since p to the 1 fully divides 2 to the n minus 1, by which, we mean that p divides 2 to the n minus 1, but p squared doesn't. Let's see what it means. So I'll just I'll just move it. Right. So I get that the order of n mod p, if I call that k, the order of 2 mod p, my bad. Right? We have powers of 2. 2 to the n is congruent to 1 mod p, which implies that the order of 2 mod p, which I'll call k from now on, k divides n, right? But k also obviously divides p minus 1. I don't need to explicitly write that, but that's always true. K divides n. So in particular, I have that p divides 2 to the k minus 1, obviously. Right? 2 to the k is going to 1 mod p. But since k divides n, p also divides, 2 to the k minus 1 also divides 2 to the n minus 1. So I have this chain of divisions. P divides 2 to the k minus 1, which divides 2 to the n minus 1. But since p fully divides 2 to the n minus 1, in that there's 2 to the n minus 1 has no more than one power of p inside it. This is p times some x, where x has no prime factors of p. So p and x are co-prime. So it's just one power of p that shows up in the prime factorization. So there's only one p sitting here, and there's only one p sitting here. Hence, there's only one p sitting here. Now we sort of just excluded n, which was our funny guy in the middle who was obfuscating things. We've kicked it out. We've shown that p fully divides 2 to the k minus 1, where k is the order of 2 mod p, right? P square does not divide 2 to the k minus 1. So if you wrote down the prime factorization of 2 to the k minus 1, only one p will show up, not a higher power. Why is this good? It's good because if, p did not fully divide 2 to the p minus 1 minus 1, so, we want to show that p fully divides 2 to the p minus 1 minus 1. Say this wasn't the case. Say there was a higher power of p that divided 2 to the p minus 1. Then if I were to look at 2 to the p minus 1 by 2 to the k minus 1, which obviously is an integer, the denominator divides the numerator since k divides p. It's an integer since k divides p minus 1, my bad. K divides p minus 1 on account of k being the order. So since that is the case, and there is one more p in the, let's say for the sake of contradiction, uh, 2 to the p minus 1 minus 1 had more than one power of p. So say p square or p cube was sitting inside 2 to the p minus 1. So if I divided 2 to the p minus 1 by 2 to the k minus 1, whatever integer I would get would have one or more power of p left over. This guy, say for the sake of contradiction, is has p square or more sitting inside this in the prime factorization. Since this guy only has one p sitting inside, when I cancel, there's at least one p remaining. That's right. So for the sake of contradiction, if p did not fully divide 2 to the p minus 1, then from what I said earlier, this number would have to be divisible by p, since there is a power of p left inside the numerator. But this number, on account of the fact that k being the order divides p minus 1, is of this form. Something to the power, so I can write 2 to the p minus 1 as 2 to the p minus 1 by k whole to the, 2 to the k to the power p minus 1 by k minus 1 by 2 to the k minus 1. Right? It's a to the n minus 1 by a minus 1. It's of that form. So this is equal to 1 plus 2 to the k plus 2 to the 2k all the way up to 2 to the k to the power p minus 1 by k minus 1. Right? But modulo p, since all of these are 2 to the k, where k is the order of 2, modulo p, each of these is 1, right? 2 to the k is congruent to 1 mod p, if you recall my definition. So each of these is congruent to 1 plus 1 plus 1 on p minus 1 by k of these. This is just congruent to p minus 1 by k mod p. And since p minus 1 by k is less than p, it's a number less than p divided by another number less than p, this is not congruent to 0 mod p, a contradiction. Hence, p must fully divide 2 to the p minus 1. In that, there is no higher power of p than 1 sitting inside 2 to the p minus 1. And you divide, it's not divisible by p. And that's it. So today you hopefully have learned something about orders. Next class, we'll pick up primitive roots, and hopefully in some time we can start talking about the legendary symbol. Thank you so much for watching. Bye-bye.